Welcome back. This is lesson 1.5, projectile motion. And so we talked about 2D motion last time. This is a specific case of 2D motion where you throw, launch, drop something such that it has a horizontal velocity and sometimes a vertical velocity as well. Now, what's special about this is it's very simple. It's just like 1D motion, just in 2 dimensions. It's 1D motion. You just have to do everything twice. And so there are a few cases. One is you start at the ground and you launch it at an angle. Another one is you start up here and launch it at an angle. You start up here and don't launch at an angle. So we can go through the various cases and the general method for solving these kind of problems. What is going to be is, well, let's start with the x-axis. In the x-axis, you're just like, throwing it or something. There's no actual sustained force moving it through the air. And so there's no acceleration. This might not make that much sense to you right now because we didn't talk about forces, but just keep in mind there's no acceleration in the x direction. It's not speeding up in the x direction, it's just maintaining its speed. And so for the x direction, what we're mainly going to be focusing on is delta x is equal to vix delta t. The vix means the x component of the initial velocity. For the y component, there is gravity. It is bringing us down. It is, accelerating us at some points, decelerating us at some points. And so it's going to be delta y. This is our favorite equation of all time. VIY delta t plus 1/2 a delta t squared. Now, specifically, this is gravity, and I do believe we covered this a little bit earlier. It's going to be negative 1/2 g delta t squared. There are a few other equations we can use as well, specifically v final squared equals v initial squared plus 2a delta x. You can rearrange that for gravity, or the y-axis. It's going to be minus 2g delta y, and all these are going to be y specific. So, fun stuff. So let's look at the 3 cases and see how they're different. This one, you don't have an initial x or y position usually. And so it's easier to find the displacements. You just subtract them from 0 to get the final position or whatever. In this case, it's also pretty easy. It's just there is usually a y component to the initial position. And so finding the displacement can be a bit tricky. If you start up here at 80 feet and land at 0, your displacement is going to be negative 80 feet. In this first case, it's going to be 0 feet. And finally here is also similar to the second case where vertical displacement is going to be negative, where 80 feet, 0 feet is going to be negative 80 feet. Another difference, these two are similar because you launch them at an angle. You have some angle theta, and if you have an initial velocity, vi, vix is equal to just vi times cosine theta. So this is some trig stuff that you should probably know. Viy is vi sine theta. So if you have initial velocity, you can break it down into initial x velocity and initial y velocity at this angle. And so in these equations where it says VIY, VIX, you can just plug these values in if you just know the initial velocity and angle. You don't know the separate components. And in this one, there's no angle. There's only an initial x velocity. There's no initial y velocity. So this is going to be 0. This is going to be the entire initial velocity. There are other equations that you can use. Equations to find the total time, equations to find the maximum height, when it reaches the maximum height, the range of the projectile. They're pretty complicated. I wouldn't suggest memorizing them. You can just use the kinematic equations that we know and the quantities that we know and combine them together. And so some of the practice problems we're going to do in just a minute do ask about like range or maximum height. We don't care about these formulas. We just want to use what we know. We don't want to memorize random stuff for some specific cases. We just want to use the tried and tested kinematic equations, apply them to this situation, and get the maximum height. So without further ado, let's go into the practice problems. We got 3 practice problems here. First one, there's a football thrown with an initial upward velocity of 17 meters per second and horizontal velocity of 21.5 meters per second. Very nice here. They don't give us an angle and initial velocity. They actually break it into components of initial y velocity is 17.0 meters per second. Initial x velocity is 21.5 meters per second. And almost all of these problems we're going to say ignore air resistance, so, fun stuff. For part A, how much time is required for the football to reach the highest point of the trajectory? Just like I said, maximum height and how long it takes to get there. There's a formula for it. I don't care. What we want to do is just use kinematic equations. And so it's going to be starting at the ground and going up to some maximum height. What is that maximum height? Well, one thing we can do is, what's special about the maximum height is going up and then coming back down. It's changing direction, and so its velocity up here is actually 0. It's at the top of its arc. If you think back to calculus, where you have a function, the tangent, the slope of a tangent line at the maximum and minimums are going to be 0. And so similarly here, the velocity, or the derivative of position, at the highest position is going to be 0. How can we use that? Well, we have the equation v final squared is equal to v initial squared. If we keep it in terms of y, it's going to be minus 2g delta y. Okay, that is a equation. What do we have? Everything we need. V final is 0. V initial is 17.0. We don't use both of them, by the way. It's just VIY, so that's going to be 17.0. We know G, we just don't know delta Y. We also don't want delta Y. That is part B. We don't care about that right now. So maybe we shouldn't use this equation. What about delta Y is equal to VIY delta T minus 1/2 G delta T squared. Always a nice equation. Delta Y, that's this right here. We don't know that. VIY we do know, delta T we want to know, G we know, delta T we want to know. And so that's also not going to work. We don't know the displacement. Are there any other equations that don't use displacement? Because, we don't care about that at this moment. And so you think back to your kinematic equations. What's the one without displacement? Well, it's the simplest one. V final y is equal to V initial y minus G delta T. Very easy, but that's the process. We didn't know what to use at first. We went to 3 different equations, but we didn't waste our time looking for a specific formula or using this equation, even though we know we don't need it. Anyway, rant over, back to this. You plug in your values. V final is 0, V initial is 17.0, G is 9.8. Sometimes it says you can use 10 for G. I'm always going to use 9.8 because it's more accurate. And so you just solve for T. You're going to get a T of 1.73 seconds. And so that's going to be the time it takes to reach the highest point. For part B, what is the highest point? Well, that's when we can use this equation again, our lovely equation. 0 is our final velocity, 17 is our initial velocity, so that squared is 289, minus 2 times 9.8 times delta y. We just plug this into a calculator. 289 divided by 2 times 9.8 gives us a delta y of 14.7 meters. Now we know that we start on the ground, and so that is going to be the height of the maximum point. We don't have to subtract anything. How much time is required for the football to return to its original level? So we can actually use a multitude of equations. I would suggest using this one, this second one right here. You could use this one because that does involve time, but we also don't know the final velocity. Kind of we do. It's just going to be the opposite of the initial velocity, but let's not use that. For the first one, what we can do is, the hard part about this is going to be delta T squared, so we're going to have to solve a quadratic equation, but we can do that. We know this is 0 because it reaches its original height again, so delta y is 0. This is 17.0. Time we want to find, and G is 9.8. So you can solve this in multiple ways. You can factor the equation. What you're going to get is 0 is equal to 17 delta T minus 4.9 delta T squared. There, like I said, multiple ways you can do it. If you want to factor an equation like that, you would just factor out a delta T and solve the remaining equation for delta T. Or you can actually, use the quadratic formula, whatever you want. But one answer you're going to get is delta T equals 0. That's obviously not what we want. You're going to get delta T equals 3.47 seconds. Now, if you actually notice, this is exactly twice as much as this. Since you're starting on the ground, ending on the ground, it's going to be a perfectly symmetrical flight. And so the time it takes to reach the highest point is going to be half of the entire time you want. But you're probably going to want to use this equation in the actual problem because they're not going to just believe you when you say, hey, it's just twice as much as this. D, how far does it travel horizontally? Now, we ran out of space on the board, and so unfortunately I must erase our previous work. But this is another thing I said, range of a projectile, that's how far it travels horizontally, and so we can work with that. What equations do we know? Now we're only talking about the x-axis. And so we can say something like delta x is equal to Vix delta t. We already know delta t is 3.47. That's how long it takes to finish its path. And so what you can do is multiply that by our value for Vix, which is 21.5, times 3.47, gives us a delta x of approximately 74.6 meters. And that's going to be your range of the projectile. That wasn't so hard after all. Moving on to the second problem. Well, actually, no, I forgot part E. Draw xt, yt, vxt, and vyt graphs for the motion. All right, not my favorite thing to do, but sometimes they're going to ask you to do this. So if you have xt, you know that, okay, it's probably going to be easier to start with the velocity graphs. Right, so I'll just draw all these graphs. For x velocity, that's going to be constant, right? It's just going to be 21.5. And so you're going to get this kind of graph. So, and we know initial position for x is 0. And then we know velocity is constant, positive. And so it's going to be a positive linear relationship for x. For y, we know it starts positive at 17, and then it goes all the way negative because of gravity. And so it's going to go all the way down there. So this is going to be a quadratic relationship for y velocity. You know, initial velocity is positive, meaning initial slope is upward, but you know overall acceleration is negative, so concavity is downward. And so it's going to, we also know it starts at 0, and so it's going to look something like that. We can actually stop it at this point because we know it can't go underground, and so it's going to end back at y equals 0. So those are going to be your graphs of motion. Obviously, on a test, if they give you a grid, you want to sketch actual points, like with coordinates and stuff like that. This is just a brief sketch. Okay, for this one, it's a biological application. So there's this insect, a froghopper, that leaps at an angle of 58 degrees above the horizontal. Okay, again, this is type 1, where it's starting at the ground and going 58 degrees. And it reached a maximum height of 58.7 centimeters. What is the takeoff speed for such a leap? So there are a few ways we can do this. First, I'm actually going to convert this to meters. That's going to be 0.587 meters. Because we want our speeds and stuff to be in meters per second. Let's see what we can do. We know the velocity at this point is 0. That could be of use. We know that delta y, we don't know time, so we, could not care less about time. We can do v final y squared is equal to v initial y squared minus 2g delta y. V final is 0, v initial is what we want to know, and 2g is 9.8 for g, and y is 0.587 meters. And so we can just move that to the other side. 2 times 9.8 times 0.587 gives us a value that we take the square root of to get the initial y velocity. And that's going to be 3.39. Now, that's not our answer. It wants the entire takeoff speed. We only know the y component of the speed. But we also know the angle is 58 degrees. And so with that, we can find the total speed using trig. We know that sine of the angle is equal to 3.39 over the total velocity. And so you just have to move it around. You get VI is equal to 3.39 over sine of 58 degrees. And again, we're going to want to use our calculator for this. Make sure your calculator is in degree mode. You're going to get 3.997 or approximately 4.00 meters per second as your velocity, takeoff speed. And what horizontal distance did it cover? Okay, so this is range again. We know the initial speed. We know we can use the equation delta y equals vi. Well, actually no, that's not a great equation. I was gonna say delta y equals viy delta t minus 1/2 g delta t squared, but we don't care about time at all in this. What we do care about is delta x. We also care about initial. And, we don't really care about time, but as it turns out, we're going to have to use time. The thing is, if we begin with this, we can find out time, and then from there, plug it into this other equation, delta x equals vi x delta t, and solve for delta x. So, two-step process. For this first one, we plug in 0 here. vi y we said was 3.39, and that's 9.8. And so you get another quadratic equation that you want to solve. This one's going to be 3.39 delta t minus 4.9 delta t squared equals 0. Again, multitude of ways to solve for it. But if you solve, you're going to get t equals 0, obviously, and delta t equals 0.691 seconds. That's not what we want. We want delta x. And so that's going to be equal to the velocity is 0.691 times the initial horizontal speed. We didn't calculate that, but we know that it's equal to vi cosine theta. So vi was 3.997 times cosine of 58 degrees, and that's going to give us 1.463 or 1.46 meters. That's it for that problem. And our last problem of the day. You got a man sitting on a roof. So this is going to be not on the ground. You got a man sitting on the roof, throws a rock with a speed at an angle. So it's not going to be just flat downwards. I wish we could have done a problem like that, but only 3 problems for these review videos. Here, you're going to stand up here and throw at an angle of 33.3 degrees. Speed is 29.0, so we can calculate vi x and vi y. The maximum height above the roof that the rock reaches. Okay, so we can use projectile motion formulas. First, let's calculate the equation. Delta y equals vi y delta t minus 1/2 g delta t squared. Well, we don't want time, so let's look for another equation. What equation doesn't have time? That's going to be v final y squared is equal to v initial y squared minus 2g delta y. And here we know g is 9.8. viy we can calculate using 29.0 times sine of 33.3 degrees. And v final is 0. And so you just move everything to the other side. You're going to get 29 times sine of 33.3 gives us approximately 15.9. So that kind of makes sense. And that's going to be divided by 2 times 9.8. And that's going to give us our delta y is going to be 0.812 meters. Now, that's not the entire height because you're standing at a certain position, and so you want to add the initial position to it. So this is just the displacement. So it's going to be 16.2 meters as our answer. Part B, the speed of the rock just before it strikes the ground. Well, how can we do that? Well, again, v final squared equals v initial squared minus 2g delta y. Same exact equation. We already know viy squared is 15.9 squared, and we know 2g 9.8 is g. Delta y is going to be negative 15.4. Keep the negative in mind because you're starting up here and then going down here, so that's a negative value. So plugging it in, you have this 15.9 from the viy. You square that minus 2 times 9.8 times negative 15.4. That gives us a really big number. We have to take the square root to get v final. That's going to be 23.6 meters per second. Now, that's not the entire speed because there's also the v final x. And what is the x component? So that's going to be 29 times cosine of 33.3 degrees, which is approximately 24 meters per second. And so to find the total speed, you just, magnitude of this. You do x squared plus y squared, so 24.24 squared plus this 23.6 squared. And that's going to be a total velocity of 33.8 meters per second. Now it's actually negative, but we want the speed, so speed's always positive. Last part, horizontal range. Okay, that was pretty much expected. We know vix. We don't know delta t though. So let's try finding delta t using well, we can use delta y is equal to vi y delta t minus 1/2 g delta t squared. Now, this one's going to be tricky because this delta y isn't 0. It's going to be negative 15.4. keep in mind the negative. This is 9.8, and this is that 15.9 value we had earlier. And so this time you could factor it, honestly. It's not too hard to factor it, but I would really suggest using the quadratic formula. That's going to be so much easier. Or if you have some device that can solve it for you, you're probably not going to be allowed to use that unless it's like a calculator that you are allowed to use on the AP test. But you know, just solve it using the quadratic formula. Kind of gets a bit tricky. You're going to get a negative and positive answer. It's not going to be negative. And so you're going to get delta t equals 4.03 seconds. Plug that into delta x equals VIX delta t. You know, VIX from earlier, it was 24.2. So you multiply that by this 4.02, whoops, I wrote this wrong, 4.03 seconds. That's going to give us a delta x of 97.7 meters. So that's our answer. This was our last problem for this video. This one was a really long video because projectile motion is a pretty big concept. But our last video on kinematics is our next video, which is relative motion. So I'll see you then.